All right, everyone, welcome back. Daniel will give his third talk on l-adic aspects.
Great. Okay, so let me briefly recall something from Sasha's first talk, and that also that Jake alluded to quite a bit in his talk. So X is going to be, for now, smooth and projective over K, which is a finitely generated field. And then L will be a prime, which is different from the characteristic of K. This is the setting in which l-adic cohomologies will behave. And maybe let me just remind you of some analogy, which Sasha discussed between the Tate conjecture and what he called the relative Fontaine-Mazer conjecture. So the Tate conjecture, it says the following, which is that you have a class C in H2I of xk bar with QL of I coefficients. So this is a Tate twist, which is meant to make the cycle class map Galois covariant. And you say this is in the image of the cycle class map, which goes from codimension I cycles on xk bar to this group, this tensor QL, H2I xk bar QL of I, if and only if the Galois action on K, on C rather, has finite orbit. So this is the Tate conjecture is at least conjecturally characterizes those cohomology classes in the image of the cycle class map in terms of the Galois action on this side. And then Sasha explained to us that there was an analogous conjecture in the Nonabelian setting. So maybe this is the l-adic counterpart to what I call the Nonabelian Putsch conjecture. So I'm going to call it the Nonabelian Tate conjecture. I think Sasha called it the relative Fontaine-Mazer conjecture. And let me just slightly disagree with him there and instead call it the relative Fontaine-Mazer / Petrov conjecture. And the reason why is that the original Fontaine-Mazer conjecture comes with some kind of k-adic Hodge theory condition, and I think somehow maybe the strongest evidence we have for it is that Sasha showed that in fact that the k-adic Hodge theory condition is a consequence of arithmeticity. I'm not sure if you're going to explain that in your talk, Sasha. Great, okay, so maybe we'll hear more about that tomorrow. So I won't say anything more about it. But what does the conjecture say? It says that rho, a representation pi1 of tall xk bar, let's say gln ql bar, a continuous semi-symbol, is of geometric origin. Okay, maybe now we believe that this is kind of the Nonabelian analog of being a cycle class, if and only if the Galois orbit of the conjugacy class of rho is finite. So the exact same condition. Okay, and Jake very nicely explained to us the proof of, well, more or less the proof of the did Jake actually explain this? The forward direction of this? No, maybe not. No, you told. Okay, I'll say a word about it. Okay, so the forward direction of this is pretty easy, as I'll explain shortly, and then the backward direction of this is mostly open. I'll say a little bit. Okay, and then the definition, which I think Sasha gave us some version of, is that this condition here is what is meant to be rho is arithmetic. So I think what maybe Jake did explain in the context when rho is rigid is that, so Sasha I think gave a slightly different definition of arithmeticity, namely that your representation extends to pi1 of x over some finite extension of k, and Jake's explanation of why rigid things are arithmetic, in fact, contained within it the seeds of how to go from this finite orbit condition to the statement Sasha. Okay. So before digging into this conjecture and its predictions and some evidence for it, some of which Jake very nicely explained, let me just draw your attention to sort of a situation I find very unpleasant, which is we now have two conjectural characterizations of representations of geometric origin, right? So one of them is like being a direct factor of a z variation of Hodge structure. So this is what I discussed in the last talk, and then there's also this conjecture. And we know this, like, so in particular, this condition should be like equivalent to that other condition, which, and so that equivalence makes no reference to being of geometric origin, which is like something you can never really hope to prove that some I can never hope to prove that some random representation someone gives me is of geometric origin, but maybe, maybe the conjecturally equivalent conditions could be proven to be equivalent to one another. And that's something we also don't really know how to do. And I think what Sasha is explaining is, some gesture towards that. But I want to maybe just mention that there is, I think, some kind of very weak evidence that connects this arithmeticity to what I discussed in the last talk. So I just want to mention that before kind of digging into pure l-adic statements. Okay, so here's some kind of proposition which I don't think is really in the literature, but I really like. So suppose x to s is smooth and proper. And let's now take S tilde to be the universal cover, or a universal cover. Yes, and x tilde will be the base change to S tilde. So this is all happening over C. And let's suppose V is a local system on x tilde, such that V restricted to a very general fiber. Let me give this his name, pi tilde. General fiber of pi tilde underlies the variation of Hodge structure. All right, let me just say a word about this. This is all happening analytically, so very general means on the complement of the countable subset of analytic closed subvarieties of S tilde. And the fibers of this map are algebraic varieties, it's the same as the fibers of pi. So it makes sense to ask questions like, is this V of geometric, V restricted to a fiber of geometric origin? The fibers are algebraic varieties, even though x tilde and x tilde are completely not. Okay, so what you would expect is, if this is true, you would expect to be able to show that, let's say V is a cube system. You'd expect to be able to show that V is of geometric origin, if you believe what I explained in the last talk. So we definitely can't show that. We definitely can't show that V tensor QL is arithmetic or anything like that, but maybe let me say what you can show. So if you take V tensor QL, so you can view this as this is now an l-adic local system, and Jake explained how one can take an l-adic local system on a complex variety and view it as a sort of more arithmetic object, so view it as a representation of the étale fundamental. So viewed as a local system on the geometric generic fiber of pi. So here I've base changed the algebraic inclusion of the function field of S. So then this has finite orbit under, well, what you'd expect is that if you descend this whole situation to some finitely generated field, like some number field maybe, you'd expect this local system to have finite orbit under the Galois group, that number field. But all I know how to show is that it has finite orbit under the function field of S. So I think this is the only thing I really know that directly connects arithmeticity and what we discussed in the last talk. So let me just give you a one-line sketch of the proof before digging into this thing. So proof sketch. So really, I mean, I've written things to make it look arithmetic, but there's a lie here. And just because of this C, you can translate it into the following statement, which maybe should explain sort of why I was thinking about things like finite orbits in the first talk in this series. So what you really want to show is that the pi1s action on V restricted to a fiber has finite orbit. So this is what you really want to show. So let me, yeah?
Just like, how does the Galois root of like field that's over C, how does it act on V tensor with QL?
Yeah, so this is sort of what Jake explained. I'm trying to elide this point. So the point is that this is now, so V was like a representation from pi1 of the fiber into GLMZ. Now you tensor with QL, you get or ZL, so you get a representation into a profinite group. So the representation factors through the profinite completion of the fundamental fiber, and that's the A12 fundamental fiber. And then maybe we already know how to think about Galois actions on representations of A12 fundamental groups. But here I've now translated this sort of arithmetic-looking statement into something much more innocent. So really, all you care about is, well, maybe you know how pi1 of the base set has an outer action on pi1 of the fiber. So you just take a loop in the fiber and drag it around. Okay, so let me just say a word about why this is. So what you can do is you can look at let's consider the following set. So pi tilde inverse of our base point S. Sorry, this is not what let me give this name F. Let's consider F inverse of S. So this is the set of points in the universal cover which map to our fixed base point. And for each one of those, we get a local system on XS. So for all, let's call it S prime in F inverse of S, we get a local system VS prime on XS. Why is that? Well, we have a local system on X tilde, we can restrict it to each of the fibers over these S prime. And those are all just the same as XS. This X tilde is base change from X. Right, so, okay, and this assumption means that these all underlie ZVHS. Right? Okay, now you have to unwind something. Well, these VS prime is precisely the pi1 SS orbit of V. So the statement is just unwinding how pi1 of the base acts on local systems on the fiber. Okay, but now here's a beautiful theorem of Deligne. So the set of isomorphism classes of rank R Q local systems on a smooth, let's say a smooth projective variety, smooth quasi-projective variety. Over C, which underlie ZVHS. And I should have said, yes, smooth rank R local systems is finite. Okay, so this set is finite, so this set is finite. So, okay, and of course I'm outsourcing all the work to this beautiful theorem of Deligne, which you can ask about after the talk. Okay, so I just want to indicate that at least there is maybe some kind of very weak connection between this conjecture and what we discussed in the previous talk. Okay, so let me now just start, there will be no more complex geometry in this talk. Let me start just trying to draw some connection, some consequences from this conjecture. Are there any questions about what I just explained? So we'll talk a little bit more about this in the next talk. Okay, so let's talk about just some predictions of this Nonabelian take conjecture. Okay. So the first prediction is the one that Jake explained to us, which is this conjecture of Simpson, namely that rigid local systems are of geometric origin. Okay, and as Jake explained, this itself makes many predictions, right? So what you can do to find evidence for this conjecture is you take any property of a local system of geometric origin, and then you try to show that a rigid local system satisfies that property. So, for example, it should be a direct factor of a ZVHS, right? And I think Jake explained that Simpson and in the quasi-projective case Mochizuki showed that at least we know you're a direct factor of a QVHS. So maybe let me just say what's left over. Well, you have to show, to go from being a direct factor of a QVHS to being a direct factor of a ZVHS, you have to show the monodromy and find over the ring integers of a number field. Define over, okay, for A some number field. And so the main point of this talk will be to describe the proof of this statement for cohomologically rigid local systems. Jake mentioned to us, so the theorem of Esnault-Groechenig is that cohomologically rigid local systems are integral in this sense. Let me just define integral, just so I don't have to write this long phrase to define the ring of integers of a number field. And I'll discuss this further. So most of this talk will be spent proving this theorem, but maybe let me remark, which is that like implicit in the statement of this theorem and the way Jake formulated it is, so what he said is you have a local system with finite determinant, and you look at deformations of the local system which fix the determinant and maybe fix some conjugacy classes at infinity if you're in a projective setting. And so there's sort of a group implicit in the statement, namely you look at the determinant, you look at the group of all matrices with determinant, let's say, of some order, so for example, trivial determinant via SLN, and then you look at deformations of your representation within SLN. And it's very natural to ask the same question with another group, like what if you, instead of saying SLN, you say SP2G or something like that, and this is actually a theorem of Abdal and Patricus, both of whom are, well, you all know to be here. This is also true for G cohomologically rigid. Rigid local systems. Which just means you replace, so in Jake's description of cohomological rigidity, there's some vector space, and that N0, that vector space is the Lie algebra of SLN. And you replace that vector space with the Lie algebra of the group which you have. But I won't say anything more about this. Okay. So we'll come back to this theorem. So I'm going to more or less explain the proof of this theorem, taking as input some deep work of Horg and Deligne and Drinfeld. Let me make some, before I do that, let me draw out some other predictions of this conjecture. So before I do that, are there any questions about this? Yeah. Yeah, so there's some group G in the picture, so instead of a representation of GLN, you put a representation of G. You can equally well define a character variety for G representations. You just replace GLN in the definition of an representation set with G, and then you ask that your representation be a reduced isolated point of that variety. So in other words, you're only looking at deformations which stay within a fixed, possibly smaller algebraic subgroup of G. Okay. Great. So okay. So how does one draw consequences of this conjecture? Well, again, you look at features of representations of geometric origin, and then you try to like say, well, if you're arithmetic, well, maybe you should have those features. Right. So okay. So one feature of a representation of geometric origin in this setting, where I'm taking like l-adic cohomology, is there's this prime number L, right? And that's a choice. You can choose a different L. So in particular, if you look at variety, you can take its L1-adic cohomology, and you can take its L2-adic cohomology, where L1 and L2 are two different primes. And there's some relationships between those. Right? And so what you should predict is that if you have an arithmetic l-adic local system and some other prime, well, this was the cohomology of some variety, supposedly, if you look at this theorem. So you could take the cohomology of that same variety with QL prime bar coefficients. And then you should predict that there exists some other representation which is related to this one, namely the cohomology of the same variety. Okay, so let me state a rigorous conjecture. This is a conjecture of Deligne. So I'm going to state it more or less the way he stated it. So suppose that x over fq, fq is a finite field, is a normal variety. So L is not equal to the characteristic of fq. And let's suppose E is an irreducible QL bar sheaf, so QL bar local system, on X with finite determinant. This is in the same sense that Jake was describing. The determinant is some one-dimensional representation, and I want some power of that one-dimensional representation to be trivial. So then the conjecture has three parts. So first of all, there exists some number field, E, inside of QL bar, such that, actually, let me start numbering it after this. Then, such that 1, for all closed points of X, so I'm going to use bars around X to denote the set of closed points. Well, given a closed point of a variety over fq, it has residue field fq to the n for some n. So you get a map from spec fq to the n of your variety. In particular, you get a map from the Galois group of fq to the n, pi1 of the variety. And that has a Frobenius in it. Right, so what that means is that for each point, you get a Frobenius action on E. So let me extract some data from that. So what you get is that the determinant of 1 minus fx t, so fx is the Frobenius element at x. This acts on ex, so the fiber of e at x, and you want this characteristic polynomial to be a polynomial over e. So it's saying the characteristic polynomial of these Frobenius elements have coefficients in a number field, and not only that number field can be chosen independently of the point. So let me kind of say why this is a prediction of this conjecture. Well, the fact that your local system is on x over fq means, well, the corresponding representation is extended from pi1 of xq bar to pi1 of xfq. In particular, it's arithmetic. So it should come from geometry. It's the cohomology of a family of varieties. And, well, what happens when you take the cohomology of a family of varieties? These characteristic polynomials of Frobenius count points on the fiber. So in particular, if you take the whole cohomology, those characteristic polynomials should live in Z adjoint T. And here we're saying they live in, well, you took some n, so now they only live in E adjoint T. So 2, so for all places, lambda prime of this number field E, not above characteristic of fq, there exists an E lambda prime prime with the characteristic polynomials of the Frobeniii on this E prime equal to the characteristic polynomials that we started with. Okay, so this is exactly what I was saying before. There was a choice here if you believe that this E comes from geometry of the prime L. And so if you'd chosen a different prime, so if you're taking the cohomology with coefficients in QL prime bar, or L prime difference, if that's this lambda prime, you could take the cohomology, but you'd still be counting points on the same family of varieties. So these things should match. Okay, and then third, and I won't really say anything else about this, so the roots of the determinant of this, the roots of this characteristic polynomial should be integral over z adjoin 1 over the characteristic of Q. So again, this is some property that is satisfied if E actually does come from geometry. Okay, so what did we do here? We said, well, having a sheaf on X over FQ means it should come from geometry, and then we just said, well, what can you do with sheaves that come from geometry? You can count points on the fibers of your putative map Y to X that the sheaf came from. Those should, the number of points on a thing should be an integer. That's where this comes from. You could take cohomology with different coefficients, and while also the Frobenius eigenvalues should behave like Frobenius eigenvalues on the cohomology of the family. Are there any questions about this? Yeah.
So, as you said, if it comes from the cohomology of a variety, then you can in fact take E to be Z.
Yeah, so if instead of taking a summand, if you took the whole cohomology, you could take E to A as E to Q the way.
And here you're taking summand in what sense?
So you're taking it, so you're supposed to imagine there's some Y to X, and you took the cohomology of the future Ri pi lower star. That's some local system on X, and I took a summand of that local system.
No, I'm thinking about what happens to our coefficients that are not to consider here.
Oh, just in general, if you take like let's suppose you have a representation of a variety into, a representation of a group into GL and Q. When you go up to Q bar, not all the summands might be defined over Q. You might need to test some summands.
Q bar there is not.
Yeah, QL. Yeah.
Some of these statements resemble statements like conjectures. Where the hypothesis components in this conjecture.
Yeah, and that's an exactly theorem.
Okay.
Yeah, so you can write more. Yeah, so this is, in fact, this is conjecture Deligne makes in his V2 paper. It's part of the companions conjectures. I'll say in a word what's known about it, but quite a bit is known. So in particular, that statement you just made is known. I mean, I should say this finite determinant business, it makes the absolute values of the eigenvalues maybe a little less interesting. All right. Okay, so maybe let me make a remark about this conjecture, which is that it's sort of mostly known. So the reason that it's a conjecture is because of that word normal. So this is conjecture theorem. So Laforgue proved this when the dimension of X is 1, and it's a consequence of his proof of the Langlands program of the Langlands program for function fields for GLN. Okay, what's the point there? What he really does is he actually proves this conjecture for curves over finite fields. So part of his proof is to find arithmetic local systems on a curve inside of the cohomology of some stacks. So I won't say more than that. And then it's a theorem of Laforgue, Deligne, and Drinfeld if X is smooth and the dimension of X is bigger than So in fact, in the setting we'll be in, you might as well take it as to be. You can think of this as a theorem. We're only in this conference we're only thinking mostly about smooth varieties. Okay. So I actually do think there are some really genuine obstructions to proving this 1x is normal. I think it's very interesting and we somehow don't understand it. Okay. So maybe let me make one more remark about this, which is, so this condition on characteristic polynomials of Frobenius might seem a bit funky, like maybe it's motivated by the Bacon conjectures or something. But one way to think about it is that the characteristic polynomials of Frobenius, so these polynomials, so these determine E completely. Well, because I said E is irreducible, maybe let me say in general up to semi-simplification. And this is by the Chebotarev density theorem. So somehow this condition 2 here is going to pin down at most 1 E prime. But there's a warning, which is that, okay, I told you this is a theorem and that you kind of pin down for each E at most 1 E prime then. So you might be tempted to believe there's some kind of functor from like QL bar local systems to E lambda local systems or something like that, or E lambda bar local systems, and it's not a functor. It's just some kind of bijection. And you should be suspicious of anyone who tells you that it's a functor, because this category, the Hams are like QL vector spaces, and the category of QL prime vector spaces. Probably don't really expect a reasonable functor between the two. Are there any questions about this?
The second part is, I suppose, not going to
Yeah, so it goes by reduction, so by reduction to curves. So it still very heavily relies on this workable form. But so what is the kind of thing you have to do? Well, you have, let's say, some local system on X. For each curve in X, you can find one of these E primes, so we call them the companions, and then you somehow have to show they glue. It's not at all obvious that you can do such a thing. Yeah.
So in this conjecture, what is the assumption that it's actually like saying it's over the vector?
Yeah, so here it's the X is over FQ, right? So you have a local system on X, not just XFQ bar, that's what it means for the restriction to XFQ bar to be arithmetic. It means that it comes from FQ. Okay. And maybe let me make one more remark, which is that I think probably you've noticed this, which is that I restricted to X over FQ. But this Nonabelian Tate conjecture, relative quantum Maser/Petrov conjector, is over any finitely generated field. And so probably you should believe this sort of thing holds over finitely generated fields too. I just heard it this way because this is what the actual conjecture. Yeah.
So it's arithmetic even if you don't assume the finite determinant, right?
Yeah, that's correct.
So
So the finite determinant is just to these conditions 1 and 2 and 3 are all about the eigenvalues of Frobenius, right, which live in the non-geometric part of the fundamental group. So you need to normalize somehow to make those. Any other questions?
I just want to know the theorem you stated. Does it only use one direction or?
Yeah, it uses the proof, right? So yeah.
I just wanted to make sure it's
Yeah. So what you have to do is you have to show what he's actually proving this, right? And so what he shows is that given a local system like this, it shows up in the family of varieties. So I guess it's part of the Galois automorphic approach.
So you can do something like this with like general groups.
Something like this with general groups.
There's some part.
I mean, I think. Oh, you want to know like what is the? Can you control the group in the like the Zariski closure of the monodrome in the companion?
Oh no, sorry. Like I was thinking about something along the lines of like generating G to other groups.
Yeah. So I think but Whereas you can do something like you start with a group, you put it in GLN, you take a companion, and then I think what you're asking is can you control the monitoring representation of the companion? And there's a lot of work on this kind of thing. But I don't know if people think about it by using the Leyland's program for function fields over other groups. But yeah, maybe there's some experts here. I don't know, Stefan, do you know the answer? Yeah. All right. So what I want to explain in the latter half of this talk is how this theorem implies this theorem. But before I do that, let me just make one more prediction, which is coming from the conjecture I'm erasing, which I think is really interesting and which I'll talk more about in the next talk. So this is one more prediction. So here we have this Simpson conjecture, we have this companions conjecture, and so let me draw one more consequence of this relative Fontaine-Maser conjecture, which is, so suppose I have x to s, let's say over C, smooth and proper. And let's suppose, so V, let's suppose is a local system of geometric origin on just one fiber of this map, so on X sub S. So I want to point out that this relative Fontaine-Maser conjecture gives a prediction for when, if you pass to a nearby fiber, well, this is a smooth proper map, all the fibers are homotopy equivalent, so if you have a local system on one fiber, you get a local system on any nearby fiber. And I want to explain a prediction for when it has geometric origin. So let me say it this way. So suppose the pi1 SS orbit of V is finite. So this is some purely geometric condition, which we've seen many times before in my previous talks. So then two things happen. So first of all, the first one is pretty much automatic. So there exists some S prime to S, let's say dominant étal, such that V extends to XS prime. Okay, so this is just another way of saying that the local system is finite orbit. So more or less what you do is you pass to some cover where the orbit is trivial. That essentially means that it extends to the total space of this family after passing to that cover. It's not literally true. That's what you should think. So this makes no reference to being of geometric orbit. This is about being semi-simple with finite orbit. Okay, and then the interesting part of the conjecture is that be restricted to a general fiber of XS prime over S prime is of geometric origin. So I claim this relative Fontaine-Maser conjecture tells you that you can check if something is of geometric origin by checking on one fiber and checking this kind of global condition. Okay, so let me just verbally say a word about why this follows from this relative Fontaine-Maser conjecture. So what do you have to check? You have to check that this V has finite orbit under Galois. Let's say like the Galois group of the generic point of S over some finitely generated field, which it descends. So that Galois group has two parts. One part is more or less the fundamental group of S, and the other part is the Galois group of your finitely generated field. And so we've taken care of the fundamental group of S here, we finite orbit there, and now there's this Galois part, but that Galois part is insensitive to which fiber you're on. So that's something about your ground field. So the fact that V itself comes from geometry means that it is finite orbit under Galois, and then So I'll say more about this conjecture in the next talk. I think somehow, of all the conjectures I've listed, like they're all sort of impossible. But this one I think plausibly one can say something about, because you have some geometricity to start with. So you should think of this maybe as some kind of variational version of the hot-object conjecture. That's not ideal. Yeah.
This is part 3 part is there a topological proof?
Sorry, say it again?
Is there a topological proof of what you mentioned for part 3?
Wait, this?
No, that.
Oh, this thing. This is a very open conjecture, and this is a conjecture.
This is a conjecture.
Yeah, sorry, this is, let me call this the Nonabelian variational conjecture or something.
And then in this part 1, this is finite inequality. Is this sort of taking the subgroup of Taiwan which stabilized?
That's more or less right. It's not literally right. So this is just dominant étale, not finite étale. So what you do is you pass to some finite étale cover, the more or less the stabilizer of the action here. So exactly the same argument Jake explained for the local system tells you that V extends to a projected local system when you do that, and then maybe you have to pass to some further dominant étale thing to lift from projective to honest local systems. So that's
Is part 1 also conjecture, or is it?
part 1 has no. It's just a state. Part 2. Part 1 is
part one is
automatically this. If V is semi-simple. Yeah. So yeah, you don't get any points for proving part 1. Part 2 would be very interesting. Okay, and again, I mean, what you should think about this conjecture is like it's very hard to prove things are of geometric origin, but it makes predictions. So for example, you should take in a condition that's supposed to be equivalent to being of geometric origin, like being a ZVHS. Suppose you know it on one fiber, then you should know it on every fiber. In fact, that statement is a theorem of Kessler-Pentev, Jost, Zuo, and Machizuki. All right, so for the rest of the talk, oh good, I think I have just enough time. I want to give you some idea of how how the theorem I erased implies this theorem of Esnault-Groechenig. So let me put the theorem back on the board. So this is now a theorem of Ford, Deligne, and Trinfeld. Smooth. And I want to give you some idea of how it implies this theorem of Esnault-Groechenig. Before I do that, are there any questions?
Just a quick question about regarding the system part of it.
Yeah.
So like for examples where it's like examples of like local systems that are rigid but homologically rigid.
That's a great question. Okay, are there any?
Or there are, right?
Well, that's a good question. So let me say, yeah. So here's a question: is there anything left to do? Is every rigid local system cohomologically rigid? Okay, so there's a paper a very nice paper by Esnault-Groechenig and Jong where they produce a local system which is rigid but not cohomologically rigid. So the corresponding point of a character variety is not reduced. However, if instead of looking at it as a GLN local system, you look at it as a G local system, where G is this risky closure of the monotomy, it is cohomologically rigid. So as far as I know, we do not know any example of a local system which is rigid but not G cohomologically rigid, where G is this risky closure of the monotomy. So probably they exist, but it's a very annoying state of affairs. Yeah. Does that answer your question?
Or I just wanted to ask for the examples like integrality can be checked some other way. Or
There's no examples, so yeah. There's really, I mean, there's no example that's not covered by this theorem that we know of. By this couple.
So this theorem says integrality.
Yeah. So I should say like this Esnault-Groechenig is not the first result of this form. So for example, in rank 2, we know that rigid representations are even of geometric origin. And so I think I mentioned this. This was the part of this Corlett-Simpson theorem that I mentioned yesterday that I didn't say anything about before. Any other questions?
It's a related question. So,
Yeah.
so before you take the Jack to look at the moduli space,
Yeah.
you can just consider the representation for it itself.
Yeah.
Okay, it is
is it smooth? Like for a general X? No. Yeah, it has, we know a lot about the singularities now. So for example, if X is smooth and proper, the singularities are quadratic. But yeah. Any other questions? Yeah, I mean, if we knew it was, yeah.
Would the image of those singularities automatically give you some like rigid points?
Why?
In moduli? But
No.
it's not-
I don't think so. Like if you have a singularity, it still lives on some connected component typically. Like being rigid means that the connected component is.
You have an isolated singularity.
Yeah. Oh no, even if it's isolated, I mean it's still an isolated singularity inside of a larger component, right? Yeah, so I think if you have an isolated singularity, I think it has to be arithmetic, but probably not rigid. So I think it's actually kind of interesting to that you've discovered a new conjecture, which is that can you show that isolated singularities on the character variety are of geometric order? I think that is probably. Am I right about this, Sasha? I think this is. Yeah, but it's too hard. I think. Well, yeah. If you ask me about it afterwards, I'll say why I think it's why one will never be able to say. Well, using existing techniques, one will not be able to say. Any other questions?
Just really quick, so this G was that there is a closure.
So I'm Klepp-Dalton-Tricus proved this for any G. But yeah, it's the condition of being cohomologically rigid is weakest when you take G to be as small as possible. So you want your hypotheses to be weak. So you should always take G to be the sort of C closure convention. Any other questions? Okay, let me now say a few words about how to deduce from this theorem, and it's really sort of only more or less part 2 of the theorem that we care about, this theorem of Esnault-Groechenig. This is integrality. Okay, so let me first prove a theorem, which is, if you haven't seen this kind of thing, it's going to look like we're almost all of the way there. So here's maybe let me call it a lemma. It's due to Simpson. Okay, suppose V is rigid. So here, I'm going to work with X is smooth projective over C, and this is just to avoid a lot of the notation that we saw when Jake explained what cohomological rigidity means. So in this case, being rigid just means you're an isolated point of the sort of naive character variety, where you look at like tuples of matrices where your generators go, and then impose relations, and then mod out by GLN. And cohomologically rigid just means that H1 of the adjoint representation is 0. There's no kernel of a map to some other H1. Okay. So what's the theorem? So then V is defined over OKS, right here, this is the ring of S integers. Maybe let me write it as OK 1 over N. So here, where K is a number field, and N is a positive integer. Okay. So we're almost done, right? If you believe this lemma. Let's prove the lemma. So all we have to do is get rid of this 1 over N. Right? This is very easy. So why is this? Well, remember, so here V corresponded to some, I'm going to use my old notation, MBXR. So this is an isolated point of the character variety. So the representation variety that Jake described, modulo conjugation. Okay, so this is a finite type Z-scheme. So maybe let me say it. Let me put it this way. So it's this is a. C. So it's an isolated point of the C points of this variety, which is let me do it this way. It's a finite type Q scheme. Well, why is that? Well, how did we define it? We took GLR to some power, or SLR to some power, or maybe SLR times a finite group to some power. So those are your matrices. Where your matrices go, then you impose some finite collection of equations, which are like, some words in those matrices are the identity, and well, all those equations actually live over Q. Okay. So this is an isolated point of a finite type Q scheme. In particular, it's a closed point in its residue field. So this implies the residue field of this point is finite over Q. Okay. So we've at least found a number field. Right, so we started over C, and now we got a number field. So what does this tell you? It tells you the traces of your representation live in some finite, in some number field. Okay, and then a little bit of algebra tells you can actually define the representation over some possibly slightly bigger number field. Okay, and now why do you only have to invert finitely many primes? Well, it's actually kind of a deep theorem. Pi1 of a smooth projective variety is finitely generated, right? So in order to define this representation, you only need finitely many matrices, which have finitely many entries, which have finitely many denominators. So we've gotten to OK1 over n modulo some facts about the character variety, like the fact that these closed points tell you the trace field of your representation. And the fact that pi1 of a smooth projective variety is finitely generated, which is, again, a little bit deep. I guess you can deduce it from the Lefschetz hyperplane theorem, or Morse theory, or other facts. Okay, so now we have to get rid of this 1 over n. Right? So I think I have just enough time to say a word about how to do this. Okay, and what we're going to use is the fact that we have a way of switching primes. So this is number 2 here. Okay, so let's choose L, which does not divide n, and then we have our representation pi1x to say GL n a 1 over n, and then we can l-adically complete. Okay, and then just like before, this factors through the profinite completion, which is the étale fundamental group of x. Okay. And then, so Jake explained to us that under this rigidity assumption, this representation is actually arithmetic. So this actually extends to pi1 of x k. Let me even say, I'm going to do a slightly surprising maneuver here. I'm going to pass to some finitely generated, some model of x over R, where R is a finitely generated Z algebra. So I think Jake explained why we can do this with a finitely generated Q algebra, but it's a little extra maneuver to get a finitely generated Z algebra, and I won't say anything about it. Okay. So this is arithmetic. So I've again used the rigidity hypothesis. Okay. Okay, now let's pick some prime P in spec R, which is not above L, and reduce mod P. So now, inside of here is pi1 étale of x P. Right, so this is now a variety over a finite field. Okay. And now what are we trying to do? We're trying to get rid of this integer n. So it would be very nice if we could produce a representation into GLN QL bar prime, QL prime bar, where L prime actually divides that. Right, if we could find an integral model of this representation over ZL prime bar. Okay, so let me say a word about how to do that. So now let's pick, let's pick a place. So there's a number field E, such that Frobenius traces these characteristic polynomials line E adjoin T, and let's pick a place L prime, lambda dividing L prime dividing n, a place L E. And now I'm going to try to use this part 2 to produce an L prime-adic representation. So my theorem 2, from part 2, there exists a representation pi 1 etal xp to ln e lambda bar, hopefully lambda bar, which is a companion to rho, which means that this characteristic polynomial business matches. Okay. Okay, so now. Oh, so lambda is a place of this number field E, which lies above our fixed L prime dividing n. So what are we trying to do? We're trying to produce some integral models of this representation over primes dividing n. Okay, so let me kind of verbally say what we would need to be done. So here we've produced for ourselves, I have a lot of freedom to choose these L's and P's, if we choose everything sufficiently nicely, I claim we've produced a map from cohomologically rigid QL bar representations to some very mysterious QL prime bar representations, E lambda representations. So if we knew, I claim if we knew that map was injective, we'd be done. Well, why? So first of all, QL bar and QL prime bar for L and L prime different primes are isomorphic as fields. That means there's the same number of cohomologically rigid representations of this group over those two fields. So in particular, if you have an injective map between them, it has to be a bijection. Great. So second of all, these representations, they're representations of profinite compact groups. So they always factor through a maximal compact here, in particular, they always have an integral model. So if we've shown this map as injective, okay, there's a little bit of yoga involving specialization that I'm omitting here. What we'll have shown is that all of the, over any L prime dividing n, there's an integral model of your given representation. Okay, so what do we need? So we need two things. So we need that this representation, let me call it rho lambda. Rho lambda is cohomologically rigid. Okay, and we need that if we make the choices here, so we choose, for example, E a sufficiently big number field, P sufficiently big to avoid some bad primes coming from the finite collection of rigid local systems, and so on. Well, we've made a map from cohomologically rigid QL bar representations to, so given one, cohomologically rigid Q E lambda bar representations. And we need that this map is injective. And let me erase the theorem I'm proving. So let me say why this is true. So 1 is controlled by H1 of X bar with coefficients in the trace 0 endomorphisms of rho, or rho lambda if you'd like. So being cohomologically rigid means that this thing is 0. 2 is controlled by H0 of xp bar with coefficients in Hom, rho 1, rho 2. Right here, these are two different representations, so these representations are the same if this group is, if this H0 is non-zero, and different if it's 0. Okay. So now X is a smooth proper variety. This is something that simplifies the argument a little bit. So these, so the cohomology of a pure local system, which is, okay, now I'm using a deep fact here. Oh, I should have written here. It's pure. Cohomology of a pure local system is pure. So again, so the claim is that the dimensions of these vector spaces can be read off from the zeta functions of these local systems, namely generating functions for these characters or products of these characteristic polynomials. This is by I guess the Lefschetz fixed point theorem, and this in particular implies they're independent of lambda. Right? Why? Well, that's exactly what's hard to. And that's, I'm out of time, so maybe I should stop there.
Just to clarify myself, the statement before,
Yeah.
you're saying E, so the sheet doesn't depend on
So here I'm saying,
E
yes,
is pure or
E is, yeah, so E here is pure of weight 0. It's really the statement. So, yeah.
E didn't depend on the number.
Oh, this is this E. Sorry. Your local system. Any other questions? Yeah, so the weights of the eigenvalues of the Frobenius eigenvalues all have absolute value 1 for any embedding of E into the system.
Why is it weight 0?
It's this finite determinant function.
And what are the row 1 and row 2 in the statement 2 by the H0?
Yeah, good question. So you're trying. I've produced, okay, in some slightly fuzzy way, meaning there's a lot of choices involved. Some map from QL bar representations to E lambda bar representations, and I would like to show that map is injected. That's the content of the argument. So what that means is that if I have 2 distinct row 1 and row 2s, and I look at their companions, I need those to be distinct. Right. So what does it mean to be distinct? It means that this space of global sections is 0. So I would like to make sure that if that's true before on the L side, it's true on the lambda side. Does that make sense?
You're talking about 2 different spaces of E. Sorry, is it row
Yes.
1, row 2, then the image?
So I take row 1 and row 2. Yeah, it's a good question. So I take row 1 and row 2, 2 QL local systems. Suppose they're distinct. So this is 0. Then I take each of their companions. So let's call that row 1 lambda and row 2 lambda. I need to show that the analogous space with the lambdas here is also 0. But my claim is that the dimension of this space is a numerical invariant, which is controlled by these polynomials.
Okay, if there's no further questions, let's thank Daniel.
Yeah. This is because this is a finite, again, a finite case.